Friends, now it's time for the real core of the chapter, understanding what a function is. Till now, we have understood relations. Before that, we did sets so that we could understand relations in a better way. Now it's time to understand what a function is and what the difference between the relation and a function is. So first of all, let's start with the basic definition, the most simplistic definition of a function. And a function is defined as a correspondence, as a law, as a rule which basically connects each element. Now each is a keyword, each element from the set A, which is the first set, with a unique element in set B, right? So I'll repeat this particular statement. If you remember the introductory video with which we had started this chapter, all these keywords were very important and you need to refresh your memory with that, or rather see that video and connect things over here. So basically, coming back to this, the definition of a function goes as such. A function is basically a correspondence or a rule or a law which basically connects two sets. So let's just draw two sets so that we can understand. This is set A, let's say, this is set B, let's say. So this is set A, set B, and a function is basically a correspondence or a rule or a law which connects each element from set A with an unique element in set B. So this is the input set and this is the output set. So a function is defined as a rule which connects each element in set A with a unique element in set B. So this definition is very crucial. Now, on the basis of this definition, let's first have symbolic representation of how a function is. Like in relation, capital R was the alphabet which was frequently used to represent a relation. In functions, naturally it is the alphabet F. So what we generally use is this. F is a function which connects set A to set B. This is how we generally write. Now, given that A is an element of set A and small b is an element of set B, then now after understanding that A is some element from set A and B is some element from set B, then function F has elements in the form of an ordered pair A comma B. So if F is a function which has a particular law, has a particular rule connecting elements from set A to set B, where small a is an element of capital A, set A, and small b is an element of set capital B, then a function has ordered pairs in the form of A comma B. Or we also write, now this is another generic way which is going to be very frequently used, that B, the output, is equal to the function where the input is A. So generally when we write a function as f of x, x is the input, right? So f of A is going to give you the output B. So this is the manner in which we write. Now we are going back to the definition that I just said, that each element from set A, from the input set A, is connected with a unique element from set B. Now let's try and understand this language, understand this definition, and try to break it up into key points which are going to help us understand and analyze the concept, the identity of functions in a better manner. So firstly, what was said was that each element from the input set A is connected to a unique element from set B. So firstly, as I was focusing on the word each, so that is very important over here. Each element from set A, which is basically the input set. Gradually you will understand that this is where domain comes into picture, but we'll gradually understand that each element from set A has some element in set B, which is the output set. So what we have understood here is that there should not be even a single element in set A which does not have an output. So that is the conclusion which we derived from the first statement, and the second statement says that each element has a unique output. So the original definition that I said is actually a combination of both of them. Actually, the second statement has both the key ideas. The first one is that no element should be in set A which does not have an output. That is what statement 1 says. Statement 1 says that each element from set A has some element in set B. So basically the thing is there should not be any element which does not have an output. That is the first prime condition. The second condition, again and very important condition, that each element has a unique output. What it means is that there should not be even a single element in set A which has more than one outputs, right? So as it used to happen in a relation, this was a flexible condition in relation that every input can have more than one output. So if you remember, there were many examples where we had things like 1, 2 or 1, 3 at the same time. So that was allowed in a relation and that cannot be in a function, and that is what this particular statement says, that each element needs to have a unique output. So if I am having a particular input over here, it needs to have a particular defined output. I cannot have another arrow originating from the same point and originating from the same input, that means, right? So understanding these two criteria, let's try and take rough examples with the help of sets like this so that we can understand how actually to depict these two conditions when it comes to functions and relations. So let's take a few examples, as I said. Right now, first to understand the first concept, the first condition, that each element needs to have some element in set B, right? Let me take few examples: x1, x2, x3, x4, right? Now, let me have a few outputs as well: y1, y2, y3, y4. Now, if I do this, if I connect x1 to y2, if I connect x2 to y4, if I connect x3 to y1, is this a function? If you think about it, it is not. Why? Because the first condition is being violated. The first condition says that each element from set A has some element in set B. Is that getting satisfied? No, because x4 is one element which does not have an output, and that is why this is not a relation. So we need to understand that since x4 does not have an output, this is not a relation. Now at the same time, y3 is some output, or rather an image. Now this one thing we should take from relations, the previous section that we have learned, that every input is called a pre-image and every output is called an image, right? So in this case, A is the pre-image and B is the image. So likewise, y3 is an image. Rather, I should not call it an image because it does not have its corresponding pre-image. So y3 is an element from the output set that does not have an input, but that does not matter because the condition is not on the output set. Condition is not on set B, the condition is on set A, and the condition is that every element needs to have some output. And in this case, since x4 does not have an output, this particular connection is not a function, is a relation. Now on this note, let us understand this fact that every function, right, every function is a relation, but every relation is not a function, because these two conditions are applied for a particular relation to be called a function, right? So function is a subset of the A cross B, the Cartesian product, as we had discussed earlier in relations. Even relations are subsets of Cartesian product. It can be a proper or an improper subset, but between a relation and function, these are two important conditions that need to get satisfied. Now, right now, this is not a function, but if I do something like this, now does this make this a function? If you think about it, yes, it does. Why? Because each and every element has some output. So the first condition is being satisfied. Now let's talk about the second condition. The second condition is each element has a unique output. Is that getting satisfied? Yes, it is getting satisfied. Every input has a unique output. Now the word unique here, what it means is that every element should have only one output. It doesn't mean that as you can see here, there are two inputs which give the same output. That doesn't mean that every x should have a y which is not shared by any other x. That does not mean that. Unique output here means that every input, every pre-image needs to have only one image, and that is what is happening over here. X1 has one output, Y2, X2 has one output, Y4, X3 has one output, Y1, and X4 has one output, Y4, right? And that is why this is a function. So let's write this down over here. Is a function because the first condition, all inputs have an output, so that is getting satisfied. And secondly, every input has a single output, so that also is getting satisfied. Right? So this is a clear indication of both the conditions getting satisfied. Now in the Planck's module, in the very first page of the sections of functions, there are a few examples right at the bottom of the first page given, depicting by taking the help of sets like this, so that we can understand the difference between functions and relations. I'll just like to take one example from there so that we can understand. Now let's say if you have x1 and x2 over here, and here you have y1, right? In this case, if I have this particular thing, this particular connection, so to say a relation, because every function is a relation, so I can call this a relation, but we need to understand whether this is a function or not. So let's see, each element from the domain or the input has an output, so the first condition is satisfied. Now about the second thing, each element has a unique output, and even that is happening because x1 is having one output, x2 is having one output, so even this is a function. So this is a function over here. I'll just write f, this is a function over here. Now just taking another example, in this case, let's say if you have x1, if you have y1 and y2 over here, and if I connect like this and like this, is the first condition getting satisfied? Yes, it is, because each element from set A has some output, and x1 is the only element in set A and it is having some output. So first condition is getting satisfied, but the second condition is not, because x1 is not having a unique output, it is having more than one output, and that is why this is not a function, right? So this is only a relation. This is a function and a relation both. This is also a function and a relation both, because every function is a relation, but every relation is not a function, is the key thing that we need to understand. And a few more properties that we have understood is that every function is a subset of the Cartesian product A cross B. That is a very natural thing to understand, because the Cartesian product A cross B gives us all the ordered pairs possible, right? Here you can see we have 4 elements and 4 elements. That means you have 16 ordered pairs. And here, since for it to be a function, every element can have only one output, right? So the maximum possible ordered pairs possible here are only 4. So that naturally has to be be a subset of A cross B. X1 comma Y2, X2 comma Y4, X3 comma Y1 and X4 comma Y4 are the 4 ordered pairs forming this particular function. So this is the first property that we have understood. The second thing that we have understood is that if A is an element of A, then A comma F of A, right? Now this will be an ordered pair. Let's try and understand. If F is the function that is getting applied on elements of set A, then F of A is its corresponding output depending on the function. Like as we say f of x, y is equal to f of x, depending on the function you get its corresponding output. So that will be A comma f of A, an ordered pair. This would be a subset of the function f. This is how we present it. So this is a simple enough thing to understand, not a property as such but a representation of sorts. And one more thing that we have understood, which is definitely a property, that if A comma B is an element of the function f, right? A is the input, B is its corresponding output, and at the same time if we say that A comma C is an ordered pair of the function f, then since we are calling it a function f, and since it is violating the second condition that each element has only one singular unique output, in this case it is not, because A is having an output B and A is having an output C as well, and even then we are calling it a function, then clearly B has to be equal to C. That is the only case where this particular situation is still a function, and as we can see, it is not violating now the condition that every input has a single unique output, and in this case it is having, because B and C is the same, so there's only one ordered pair, A comma B or A comma C, because B and C are the same thing. So these are the things that we have understood from the basic definition of function, these two key properties. Now it's time to go back to the animation that we had used at the very start of the chapter of the machine, and basically deriving from there, let's go on to the Cartesian coordinate system as well, so that we have a few graphs to understand this particular differentiation between a function and a relation. So let's go to the machine. Here it is back. We have the input, we have the output. Now first let's take the example of y is equal to x square. This particular equation, I clearly remember we had taken this particular example in the introductory video as well, and let's have this particular thing here. Let's put a few examples, let's put a few inputs. Let's put 0 to start with. If I'm putting 0, I'm getting 0 back. So 0 comma 0 is a particular ordered pair. If I'm putting 1, I'm getting 1 output, which is 1. If I'm putting 2, I'm getting 4. So as you can see, a few ordered pairs are already getting built. If I'm putting minus 1, I'm getting 1. I'm putting minus 2, I'm getting 4. So one thing you would observe, that here what is happening is that there are two different inputs which are still giving the same output, and that is something like this, right? Like 2 is giving 4 and minus 2 is giving 4 at the same time, right? 1 is giving 1 and minus 1 is also giving 1 in this case. As you can see, the ordered pairs are listed right in front of you, but it is still a function, right? The reason behind that is that every input is still giving you a unique output, and every possible input is definitely giving you some output. So both the conditions are getting satisfied. So the machine which represents the equation y equal to x square, this particular thing, this particular relation, so to say, is definitely a function. So you can have a few more examples. Putting 3, I get 9. Putting minus 3, I get 9 again, right? So this, my dear friends, is a function for sure. Y is equal to f of x, where f of x is equal to x square. So you put an input of x, you get an output of x square. So this thing is a function, and about the graph of this particular function, because we have already come to a conclusion that this is a function, we'll also be talking about the graph of this particular function later gradually in this particular slide only. But before that, let us take another example with the help of the machine only. This example again was there in the introductory videos to understand that there are few relations which are not functions. So let's take this example. We have this example of y square equal to x. The example which I remember was being taken in the introductory video. Y square equal to x is the equation. I am putting now an input of 1, right? So x is equal to 1, my input is equal to 1. So if I am putting x as 1, I am getting two different outputs. As you can see, I am getting 1 as well as -1. So that is something like this, right? When I put 1, I'm getting 1 and -1 both at the same time, right? So another example would be if I'm putting 4, I'm getting y square equal to 4 becomes the equation, and I'm getting 2 and -2 both at the same time. That means again this case is happening. So basically this particular equation y square equal to x, this particular machine which is based on the rule y square equal to x, is not a function because it is violating the second rule that each element has a unique output. It is not in this case because an input is having more than one outputs. Every input over here is giving you two outputs. For that matter, if I put 0, I'm getting only one output. If I put 0 in this equation, y square equal to 0, I solve, I get only one value of y, which is 0. But that is the only case where that is happening. The thing we need to understand is that if even a single input is violating this particular concept, then the entire relation becomes a no function thing, right? So basically, even if a single input is violating the concept, it becomes not a function. So we need to understand this particular thing. As we can see that we have ordered pairs where one input is having two outputs, right? As you can see 4 comma 2, 4 comma -2, you can see 1 comma 1 and 1 comma -1. Likewise, if I put 9, I'm going to get 3 and -3. So this definitely is not a function. So we have seen two examples, one of which was a function satisfying both these conditions, with the another example we saw y square equal to x, where the first example was getting satisfied, whatever you put you were getting outputs, but the second condition was being violated where one input is giving you more than one outputs, and hence that was not a function. So now on this note, as I just mentioned some time back, that we are going to have a graphical analysis of both these relations, so to say. We need to understand that both the examples that we took were relations, but the first one was a function, the second one was not. Now it's time to have them on the coordinate system. So here we have our y-axis, here we have our x-axis. So first let's take the first example, which is y equal to x square, and let's try and draw this particular graph with the help of the few ordered pairs that we had obtained from the machine, right? We know that 0 comma 0 is an ordered pair, so here's my first point. Then I also know that I have 1 comma 1, I have 2 comma 4, I have 3 comma 9, right? On the negative x-axis, I have -1 comma 1, I have -2 comma 4, I have -3 comma 9 as well. There'll be definitely a few more points on either sides, even in between as well. So gradually trying to connect these points, this is the graph that I get. Now this is the graph of y is equal to x square, right? Now as you can see, it is satisfying the condition that each element from set A, which is each input, is having some output, which is depicted from the graph as well. Input is the x-axis. If I pick up any point on the x-axis, it is having some point on the graph, right? It is having some output. Now talking about the second condition, that each element has a single output, and that is again clearly depicted from the graph. If I pick up any input, I'm just having a single output. Now to understand this thing in a better way, we have a particular test, and that test is called the vertical line test. So let me just write that down over here. Now, the vertical line test, as it itself says, we need to draw a vertical line and see whether it cuts the graph at one point or more than one point. So, if a vertical line is drawn on the graph, and if at any point, if at any particular point, like any point on the x-axis, if we draw a vertical line and if it cuts the graph at more than one point, then it becomes not a function. So basically it's not a function in that case, right? So let's try it here. We have this graph of y equal to x square, and if we try and draw any vertical line, basically any line parallel to the y-axis anywhere, as you can see I am drawing many lines as such, and all these lines are cutting the graph of y equal to x square only at a single point, and hence this particular graph, this particular function y equal to x square, as I already said it, it is a function because it is satisfying the vertical line test and only is cutting the graph at only one point and not more than one point. Now it's time to go to the second example, which was y square equal to x. So again, we are having the y and x axis already. Now y square equal to x, as the function we had ordered pairs as well, a few ordered pairs are given here. 0 comma 0 would be 1, then we would have 1 comma 1, we would have 1 comma minus 1 as well, we would have 4 comma 2, we would have 4 comma minus 2, we would have 9 comma 3, 9 comma minus 3. We can have many points in between as well. Generally connecting them, this is the graph that we get, a u which is tilted in the 90 degrees direction, basically towards your east. If u was the curve facing north, then you have to make it face east. That is the only thing. The same curve that we had in y equal to x square, but now it is sleeping in this particular direction. Now, as we can see, if we pick up any input, now in this case your domain, your input set is restricted to the positive x-axis, or including the origin. We need to include the origin. Any negative x is not valid because in the equation y square equal to x, if x is negative, it straight away gets out of the real plane, because if y square is equal to negative, you cannot solve the equation, you need to go into the complex plane. So x strictly has to be a non-negative number, so basically a 0 or a positive number, right? So as you can see, the domain or the input set is restricted to the x-axis, positive x-axis with 0. Now every element has some output. The first condition is getting satisfied as we had discussed earlier, but the second condition is being violated because every input is having two outputs. And likewise, the vertical line test is also getting violated because if I draw a vertical line, although if I draw a vertical line here, it does not have any meaning because there is no graph over here. The point is, if the vertical line test is violated even at a single point, then that basically denies the relation to be called a function, and that is what is happening here. If I'm drawing a vertical line here, it is cutting the graph at 2 points. What it simply means is there is some input which is having two outputs, as you can see through the vertical line test, and if it is having two outputs, if the vertical line test is getting violated, then this, my dear friends, is not a function. So y square equal to x clearly is not a function, is something that we need to understand. Now on this note, let's try and understand a bit more about this very equation, y square equal to x. Now can be solved basically if I square root y square equal to x. If I root y square equal to x on both the sides, what I get is y is equal to plus minus root x, right? Y square equal to x, if I square root both the sides, I get plus minus root x, y equal to plus minus root x. So I can write y equal to plus root x and y equal to minus root x, right? These are the two outputs I get. Try and understand, if I put x as 4, root 4 is 2, and here root 4 is 2 again. So I am getting y equal to 2 and getting y equal to minus 2, and that is how this particular graph is created, right? Now if you think of it, y equal to root x is only the branch above the x-axis, right? And y equal to minus root x is this branch, which is below the x-axis because it is having negative y's. Here we are having positive y's, so we are talking about the first quadrant. Here we are talking about the fourth quadrant because we are having positive x's and negative y's. So if we treat each one of these relations individually, so basically y equal to root x is this. If I treat this individually and forget about the bottom graph, then this is still a function. Y equal to root x is a function because it satisfies both the condition, it satisfies the vertical line test as well. Now on the other hand, if I forget about the top part of the top branch and I just consider y equal to minus root x, then even that is a function, right? So if I distribute y square equal to x, it is giving me two separate functions, but when I consider both of them together, it is a relation. So there is one thing that we have picked up from this. From y square equal to x, we are having two separate individual functions of sorts. Now on this note, let's take one more small example to end this discussion of functions and relations. Let's take an example of a circle x square plus y square equal to 1, right? Basically a circle with unit radius. We have the y, we have the x-axis, and this is how the circle looks like, right? Radius of 1 centered at origin. Now if you think about it, it definitely does not satisfy the vertical line test, because if I have any vertical line, it is cutting the circle at more than one point. Basically it is cutting it at 2 points, and hence this particular equation is not a function, although it is a relation because it is having a correspondence between x and y, having ordered pairs out there. But again, as we did in the previous example, if I treat this as y square is equal to 1 minus x square and square root both the sides, this is what I get. Y equal to root of 1 minus x square, one with a positive, one with a negative sign. The positive one will denote the upper branch of the circle, which will individually be a function, and this particular relation will be the lower branch of the circle, which again individually would be a function, but together they would be a relation, x square plus y square, rather specifically a relation and not a function, x square plus y square equal to 1. So this is another example as we did previously. So I hope you have understood how to differentiate between a function and a relation. Also understanding that the fact that every function is a relation because there is a correspondence, but every relation is not a function. How the vertical line test works, how these two basically ideas, how these two conditions have to be applied to understand the difference between a function and a relation. We had all these properties and the basic definition of function to start with. Now it's time to explore in detail about functions and their key properties, starting with what a domain, codomain and a range is.